Okay, everybody, welcome to this little video going through the June 2016 past paper that I asked you to look at. I asked you to look at 16 and 17, so I don't know how long this is going to take. It might end up being a tediously long video. Oh well, we'll just have to wait and see. I'll try and go through it as quickly as possible. Right then, so the first question is about, it says ethene reacts with steam in the presence of an acid catalyst to form ethanol. This is a reaction that we've done in organic chemistry, but then they relate it straight away to Kc. So when you see Kc and the word equilibrium, we're dealing with equilibrium constants. You're asked to write an expression and deduce the units, and it's 2 marks. So any mistakes, you're going to be punished really for that, aren't you? So Kc equals the concentration, so we use square brackets, of the products CH3CH2OH divided by the concentration of the reactants, of which there are 2. There is H2O and there is CH2. I'm going to use exactly the same way that they've drawn it, like that. There's no large numbers for sort of ratios or anything like that, so I don't need to do any powers up here. That's fine, I know that's right. I'm not using the mark scheme here yet, only if it's a difficult question. The units of this then will be, so the way that I work this out in class, I would say that it's moles per decimeter. I mean, I can spot the unit straight away, but I'll show you what I would do. Moles per decimeter cubed, moles per decimeter cubed, moles per decimeter cubed. I've been doing this with my other class, not with you lot. Basically, the units of this are 1 over moles per decimeter cubed by looking at this. So we've got a concentration divided by concentration, which cancel. So you've got 1 over moles per decimeter cubed, which is moles to the minus 1, dm to the 3. If you can't do that, you need to work on it because it's not very hard. That was an easy question. An equilibrium mixture was found to contain 0.7 moles of ethene. So at equilibrium, we know that there was 0.7 moles of ethene, 1.2 moles of steam, which is water, 1.2 moles of steam, and 4.4 moles of ethanol. Okay, at a temperature T. The volume of the container was 2 decimeters cubed. And you go, I wonder why they're giving me that. Well, calculate a value of Kc. So you've already written the expression for it up here. We know that Kc equals the concentration of CH3CH2OH divided by the concentration of CH2CH2 times the concentration of water. So what typically people will do is who haven't practiced these or who think it's going to be easy, they don't put the concentrations in here, they just put the values from the question and think it's going to be as simple as that. Well, no, this is a moles, so this is the number I was given, 4.4 for ethanol. We need it in moles per decimeter cubed, so you have to divide by 2. If you have a look at that, it's moles per decimeter cubed. So it's 4.4 divided by 2 divided by, where are we now? Can't find the number. 0.7 divided by 2 times 1.2 divided by 2. I just had a little bit of a panic there. Oh yeah, it is decimeters cubed. Excellent. So moles per decimeter cubed. So I just had a little check there that 2 was in decimeter cubed. Didn't have to do anything with that. If you plug all that together, for the 2 marks, even if you do all of that, you'll only get 1 mark if you get it right. If you don't, then remember to do it to 3 significant figures. So the answer is 10.5. I have just looked at the mark scheme for that. So if you don't get it to 3 significant figures, you're going to lose one of the marks, and you might be really, really good at chemistry, walk out of that exam thinking you've done really, really well, but you're only getting half marks because you weren't careful. All right, so hopefully that section was fine. This question looks easy. Right, next. This looks like a practical question, burning fuels. So you should have burnt some fuels on Dr. Halliday's side of the course. You should have burnt some things looking at enthalpy of combustion and things like that. So it's related to organic chemistry, but it's really a physical chemistry question. Alcohols such as methanol, ethanol, and propan-1-ol are good fuels. Yes, they are. A student carried out an experiment to determine the enthalpy of combustion of methanol, that's the delta HC. That's the enthalpy change when 1 mole of a substance is completely burnt in oxygen, with everything being under standard. Yeah, I've run out. Standard conditions, standard states. All right, I thought it was showing off and then it went a bit wrong. Methanol was placed in a spirit burner. So there's the spirit burner down here. Methanol was placed in a spirit burner. I know what a spirit burner is. And the mass of the spirit burner was measured. Yeah, so they measured the mass before. So they've measured the mass of this burner when it was full of fuel. The student placed 100 grams of water in a copper calorimeter. Copper because it conducts heat really, really well. And they clamped it above the spirit burner. Yes, they did. The burner was lit and allowed to burn for a few minutes. So the burner was set on fire and allowed to burn. You see what I'm thinking? I'm reminding myself here that when you burn this fuel, the level of fuel will go down. So you'll have less fuel at the end. And therefore you can work out a mass of fuel that was burned. The burner was lit and allowed to burn for a few minutes. The flame was then extinguished and a new mass of the spirit burner found. So there's it. Mass 1, mass 2, and the difference is the mass of fuel that was used. The measured temperature rise was 38 degrees C. The specific heat capacity of water is 4.18 joules per Kelvin per gram, which it always is. Figure 1 shows a diagram of the apparatus. Figure 1, a diagram of the apparatus is shown alongside a table which shows the measurements of the students recorded. I'm going to have my mark scheme up with me just so I don't have to, because my only calculator is on the phone. So let me just have a little look here. So the first thing I'm going to do then, calculate an experimental value for the enthalpy of combustion of methanol. Well, in all of these experiments, the first thing to do is Q equals MC delta T. Because what we're trying to work out is how much energy, which is Q, has been put into the water in here. So in this case, you need to always remember that M is the mass of water. So I scan this information here, and M is 100 grams. 100 grams of water with a specific heat capacity of 4.18 was taken through a temperature increase of 38 degrees C. Now, I've seen people try to convert that temperature increase into Kelvin. Well, the thing is, a 38 degrees C temperature increase is the same as a 38 Kelvin temperature increase. So that would be a mistake to do that. So what this tells me then is that we are dealing with 15,884 joules of energy. So in this experiment, this flame has burning this fuel has put 15,884 joules of energy. And that would have got you 1 mark for Q equals MC delta T. If you've used the wrong mass, again, you need to go back and really think about why we're using the mass of water here. We're working out the amount of energy going into the water. All right, the next thing to do then, I think I'm now going to work out. So this gives me joules. So the steps that I like to do with these then, if you've worked out joules, our target is to work out kilojoules per mole. So I don't want joules, so I may as well turn it into kilojoules, which is 15.884 kilojoules. So there's my kilojoules bit, but I need to work out kilojoules per mole. So on a separate calculation, I'm going to try and work out the moles. So the moles, this is now looking at this spirit burner. How many moles of methanol did I burn in this experiment? So I'm going to look at the mass difference, and it looks like I have burned 1.65 grams of methanol. If I divide that by the MR of methanol, which is 32, I end up with 0.0516 moles of methanol. So in one part of the question is working out the kilojoules of energy, and the other is working out the moles of methanol burned. So the final bit is to put those two together to get kilojoules per mole. So kilojoules per mole literally means kilojoules divided by moles. The word per means divide by. So in any Q equals MC delta T question, half of the question is working out the amount of energy that goes into the water, that's this half, and half of the question is working out the number of moles of fuel or moles of chemical that have been reacted. And then the final step, so you work out this, the final step is to work out the kilojoules from step 1 divided by the moles from step 2. It always works. It's a lovely way of doing it. So, and it says that on the mark scheme as well. You divide one by the other. So it is 15,884 divided by 0. So I'll write this in the exam. 15.884 divided by 0.0516, and that equals 308. And then the final step to do, so step 4 is to work out the sign. And this is an exothermic reaction, so you put a minus on at the end. kg per mole. Next. Suggest one reason other than incomplete combustion or heat transfer to the atmosphere why the student's value for the enthalpy of combustion is different from that in the data book. Okay, so why is it different? It doesn't ask you why it's less or more. Okay, so if you think about where we got that value from, that value we did by working out the energy that went into the, sorry, going to get that focused, the energy that went into the water divided by the number of moles. So anything that changed these values will alter the overall answer. So I've got a few suggestions here. Well, from doing this experiment, I remember saying to my class that once you finish burning, you blow out the flame and then quickly go and measure the mass. And that is because some fuel will just evaporate. So fuel can evaporate. If you think about what that means, if fuel evaporates before you weigh it, the mass of fuel will be bigger. You will think that more fuel has been burned. So you will think that the number of moles was more. So your value will be less. So fuel evaporating is a big problem. It says you're not allowed to do heat transfer to the atmosphere, but some of the heat has gone into the copper calorimeter. All right, that's not the atmosphere. Some of the heat will go into the thermometer. The data book will have probably been delta H combustion standard, so done under standard conditions, and this wasn't done under standard conditions. So there's a few, but that's the one that I always remember. So this is about, you have to have done this experiment. It's one of your required practicals. So if you don't know this experiment too well, look in your textbook. You can find it in there, but it's got all of these little details. All right. You need to measure it quickly because fuel will evaporate. You need to weigh it quickly. The uncertainty in each of the temperature readings from the thermometer in this experiment was 0.25. This gave an overall uncertainty in the temperature rise of 0.5 degrees C because there was a start temperature and an end temperature. And this start temperature, if your thermometer is accurate to 0.25, you might have read it as 20 degrees C, but it could have been as much as 20.25 and it could have been as little as 19.75. Your end temperature might have been 40 degrees C, but this uncertainty of 0.25 means that it could have been anything from 39.75 to 40.25. And this means that overall there's a possible uncertainty of, so you say you might go the temperature rise as 20 degrees C, but if you take these two, the lower and the upper here, this could be as much as 20.5 degrees C. So that's where this comes from. And it could be as little as 19.5 degrees C. Probably, there we go. So anyway, calculate the percentage uncertainty for the use of the thermometer in the experiment. Well, percentage uncertainty is overall uncertainty divided by the value that you read off that apparatus. So it's going to be very simply 0.5 divided by, what was it, 38? 38. Was it as a percentage, so you times by 100. All right. The student, again, it's in the, you just need to know this stuff. I'm going to briefly I've got this A2 chemistry. Right, there we go. Here we go. Energetics. This is Q equals MC delta T, required practical measuring an enthalpy change. So it's all sort of, this is where it's laid out. If you want to know what part of the topic is, it's energetics. So you can tick it off as you go or whatever. might inform you what you need to revise. The student said correctly that using a thermometer with an overall uncertainty for the rise in temperature of 0.5 was adequate for this experiment. So they said it correctly. Explain why the thermometer was adequate for the experiment. Now, without looking at the mark scheme, I'm trying desperately not to look. I could be cheating here, but I'm not going to. I would say that in simple terms, that thermometer tiny bit of error is the least of your worries with that experiment, because loads of heat is going to the surroundings. You've got evaporating fuel. It's just not the big issue, this thermometer and its precision. All right, when it's basically quite a bad experiment. If I look at the mark scheme, what's it say? The idea that heat loss is a much more significant thing. So in other words, don't sweat the small stuff. Why are you worrying about the precision of your thermometer when you've got a flame that's, most of its energy is going into the water, but loads of energy is going into the surroundings. All right, so it's a significantly smaller problem than heat loss to surroundings. All right, the enthalpy of combustion of ethanol is minus 1371 kilojoules per mole. Let's just unpick that number. It means it's exo because that means it's giving out heat. It's a large number, kilojoules per mole. What this means is if you burn 1 mole of ethanol, you give out 1371 kilojoules of heat. The density of ethanol is 0.789 grams per centimeter cubed. And what that means is if you have a centimeter cubed of ethanol, there's a centimeter cubed roughly, this weighs 0.789 grams. That's what it means. 0.78 grams per centimeter cubed. All right. These often throw people. So you're probably looking at this question thinking, oh, this is the one that I struggled with. We know in chemistry that if you can get the grams of a substance, you can work out the moles of a substance, and that's what we're aiming for ultimately. So calculate the heat energy released in kilojoules when 0.5 decimeters cubed of ethanol is burned. Well, 0.5 decimeters cubed is half a litre, isn't it? That is 500 centimeters cubed. It's 500 of these things. It's 500 of them. So 500 centimeters cubed. We've got 500 centimeters cubed, and each centimeter cubed weighs 0.789. So it's 0.789 grams per centimeter cubed. You'll see the centimeter cubed and the centimeter cubed cancel. 500 lots of 0.789. That will basically tell you how heavy half a litre of ethanol is. Mark scheme? Mass of ethanol, there we go. First mark is for doing that. You're turning the density into a mass. I mean, don't overcomplicate it. Grams per centimetre cubed, and you've got this many centimetres cubed. Yeah, it's a bit of a unit conversion, but it's not that difficult. 394.5. It says here that it would accept 395 because it's 3 sig figs. 394.5 grams of ethanol. I've got this many grams of ethanol. Another rule in chemistry is whenever you've got grams, turn it into moles. So I'm now going to turn it into moles by timesing by the... don't do that. Mass Mr. Moles. By dividing by the MR. So that's going to be 394.5 divided by MR, 46. That'll tell me how many moles of ethanol I've got, which is 8.576. 8.576 moles. I reckon that's worth a mark. Da-dunk. Now then, so I know how much. So I've taken this, I've got half a litre of ethanol, and all I've done there is gone, well, half a litre of ethanol is 8.576 moles of ethanol. So half a litre, I worked out how much that weighs, and once I know how much it weighs, I can work out how many moles I've got. So I know if I've got half a litre of ethanol, I've got this many moles. That's how the density has helped me. If I've got this many moles, and I know that there are this much energy, 1,371 kilojoules is given out per mole burned, all right, and I'm about to burn 8 moles of it, it makes sense to times kilojoules per mole by 8.576 moles. That and that cancel, you'll end up with kilojoules. It'll give out 11800. So what it's saying is, if you burn half a litre of ethanol, that's a lot of ethanol, that 500 centimetres cubed of ethanol, you will give out this much heat. In other words, it'll warm you up nicely. All right, so don't get confused about density. Maybe seek out as many density questions as you can, because they're not that hard. But I know that everyone will have struggled with that. Or not everyone, a lot of people will have struggled, because you're just seeing all these numbers. You've got kilojoules per mole, which says if you burn a mole, it's this many kilojoules. So it makes sense then you need to work out how many moles you've got, because if you burn 2 moles, you'll give out twice as much energy. If you burn 8.576 moles, you'll burn 8.576 times as much energy. You'll give out 8.576 times as much energy. So how do you work out moles? Well, this way, rather than just giving you a grams, they give you a density and a volume, and you work it out from there. Typically, they catch people out. If I have a little look now, I've got the examiner's report over here to the side of me on my laptop. What did the examiner say about this? So, the first question... Let's have a little look here. Sorry, just had an email through there. The first question says the equilibria one was done well. Some people struggled to work out concentrations. Enthalpy of combustion and calorimetry. The uncertainty question, some people were not very good at that. And then lots of people struggled to use the density to find the mass of ethanol. Others struggled to convert decimeters cubed to centimeters cubed, which is not on really, okay? Just remember this, 1 decimeter cubed equals a litre, and everybody should know that 1 litre is 1,000 centimeters cubed. If you know this, you know that 2 decimeters cubed is 2,000. You know that 0.5 is 500. Anyway, guys, the video's 21 minutes already, and I'm only on question 3. I might have to do this in segments, okay, or sections. Right, octane and isooctane. Isooctane, isooctane. Right, octane and isooctane are structural isomers. They are same molecular formula but a different structure. With the molecular formula C8H18, so this is what I've been doing with you. I love this stuff. The displayed formulas and boiling points of octane and isooctane are shown in figure 2. Alright, isooctane is just an old-fashioned way of naming this. So there we go, first question. Give the IUPAC name for isooctane. Oh, I haven't done this for ages. Right, longest chain, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, it's 5. So we're dealing with a pentane. Now that I know that I'm dealing with a pentane, so I'm just going to have that as the chain. I've got a methyl, a methyl, a methyl, so I'm going to go for, it's a trimethyl. Trimethyl pentane, and I now need to show the positions. So it's either going to be 244 or 224, 224. Let's get better. 224, comma, chameleon. Right. 224, didn't need that comma. 224 trimethyl pentane. I'm never going to say they're easy, because you've seen me muck up so many of them that they're not. Octane and isooctane can be separated in the laboratory. So name a laboratory technique that could be used to separate isooctane from a mixture. So these are both going to be liquids. You're given this information, boiling points are different. If the boiling points are different, you need to use distillation. You can use fractional distillation, you can use simple distillation, but here's the basic idea. You've got a flask there, you have a condenser over here, you've got a thermometer in the top there. This is a Liebig condenser with water going in there and out there. You heat the mixture up. Oops, you can see that. You heat the mixture up. The boiling point of isooctane is 99 because it's a branch chain isomer, so the molecules can't get as close to each other, so the van der Waals forces will be weaker. Anyway, what will happen first is the isooctane will evaporate first. You'll be able to read that off at the thermometer, which will say 99 degrees C. The isooctane will drip out at this end. Once all the isooctane has come over, you'll see a temperature jump to 125, and then you need to get another little beaker under here and start collecting the second fraction. Right, marks. Outline how this technique separates. Distill. Isooctane is the one with a lower boiling point. So it'll either reach the top of the column first or boil first, depending if you're talking about fractional or normal distillation. This is normal distillation. Isooctane will collect first. So I reckon. Does it say a little diagram? It says you've got to refer to laboratory apparatus, so I was using words like Liebig condenser and things like that. So anyway, next, isooctane is added to petrol to increase its octane rating. Some high-performance engines require fuel with a higher octane rating. You might have heard of the term, like for racing cars at Formula One, they call things like that high-octane sports. And it comes from the fact that they burn a lot of octane because it gives out a lot of energy per mole. So it means you can carry not that much fuel and get the most energy from it. It's a very sort of energy-dense fuel. Write an equation for the complete combustion of isooctane. Any equation starts with an arrow. If it's complete combustion, we're going to start off with O2. I'm burning isooctane, which is C8H18. It says use the molecular formula. The molecular formula means you don't need to worry about the structure of it. Complete combustion means you're going to make CO2 and H2O. Carbons first, I'm going to make 8 carbon dioxides, 18 hydrogens will make 9 H2Os, 16, count my oxygens now, 16 plus 9 is 25, so I'm going to need 12 and a half or 12.5 of them. Just check my answer, just in case I made a silly mistake, and I haven't, that's fine, 1 mark. Explain in general terms how a catalyst works. Again, I'm not going to look at the mark scheme, I'm just going to say, provides an alternative reaction pathway with a lower activation energy, therefore making more frequent successful collisions. But anyway, the mark is for alternative reaction pathway with lower activation energy. So that's cool, isn't it? You just got to learn that, haven't you? Because that question comes up again and again and again. Carbon monoxide is produced when incomplete combustion takes place in engines. Nitrogen monoxide, okay, CONO, is another pollutant that produced in car engines. Write an equation to show how these pollutants react together inside a catalytic converter. Right, CO, that's toxic. NO, that's pretty nasty and all. You react them together and it makes CO2. It ain't great, is it? Hey, is anybody else enjoying the beautiful fresh air that we're getting now during lockdown? Long may it continue. Here's to the death of the motor vehicle, the petrol-powered motor vehicle. Right, CO2 plus N2, nitrogen, that's fine in the atmosphere. How do you balance this? I just remember this is, so it's 2 of them. 1, 2, 3, 4. I just feel like I might have mucked that up. No. That's balanced, isn't it? Cool. Platinum, palladium and rhodium are metals used inside catalytic converters. A very thin layer of the metals is used on a honeycomb ceramic support. Honeycomb, if you know, you can imagine what a honeycomb looks like. It's just full of holes. Again, this is in your textbook, this specific example. It's also in the scheme of work. You need to be aware of catalysts are spread thinly on what they call support medium, a support medium. So what can happen is this is full of holes rather than being a big lump of catalyst. Why is that? So it increases the surface area to volume ratio so that you don't need as much catalyst to be used. Now, most people would get the mark for increases the surface area to volume ratio. But then I don't know if I would have got, because I just glanced down there, actually I cheated a little bit to see what the second mark was. The second mark was saying, so you don't need as much catalyst. Platinum, palladium and rhodium are incredibly expensive. You wouldn't put a huge lump of platinum inside the back of your car because only the surface of this platinum would be able to do anything. All of the inside of the platinum, I don't know what that diagram shows, all of the inside of that platinum is wasted. All right? So catalysts, they're not used up, so you only need a very thin layer coated on something to work. Anyway. 3.7. Ooh, I like the look of this. I bet this is about EZ. Maybe not. I thought it was going to be about EZ because I was looking at this double bond. I know somebody in the class who would like this diagram. Anyway. Oleic acid. Olei is a straight-chain fatty acid obtained from plant oils. Isooctane can be made from oleic acid. I just want to say olei every time I read it. The skeletal formula of oleic acid, I'm going to make something up. Oleic acid was discovered in Spain in 1972. Olei. Shouldn't have said it. Oleic acid is a straight chain fatty acid obtained from plant oils. Isooctane can be made from oleic acid. The skeletal formula of oleic acid is shown in figure 3. Alright. Identify a reagent that could be used in a chemical test. So we did chemical test. This is us. I gave you a little video to look at. Right, chemical test. So what am I dealing with? I've got a carboxylic acid here, and I've got a double bond there. A chemical test to show that it's unsaturated. Well, that's to do with the double bond, and the chemical test is bromine water. I wonder if they'd allow Br2 aqueous. I wonder. Yep, you allowed that. Bromine water, and it goes from orange to colourless. That is GCSE and easy. Right. Question 4. I think this is going to be the last question I'm going to do on this little video. I'm going to pause it and then I'm going to record another one, just to sort of break it up a little bit. Whew. Right. All of these compounds have a relative molecular mass of 58. Now they're not all isomers of one another, because this one hasn't got any oxygens in, but they all happen to weigh 58. Explain why determining the precise relative molecular mass of propanol and prop-2-ene-1-ol could not be used to distinguish between samples of these two compounds. Alright then, this is C3H12345 This is C3H6O. This is C4H10. Now all of these add up to 58.0, but if you take the very precise masses of carbons, hydrogens and oxygens, C4H10 and C3H60 do not weigh precisely the same amount. There's a little bit of a difference because this one hasn't got oxygen, and this one has. These two though have got exactly the same molecular formula, therefore they will have precisely the same relative molecular mass. Okay, mark scheme, same formula, so precisely the same relative molecular mass. We did a little bit about precise relative molecular mass or mass spectrometry at the time. It's really easy, isn't it? All right. I hope you realise that's a very easy question. All right, infrared spectrum. Yay, I love these because you should just be fine with it. I'm going to look at this. I'm not even going to read the question. I'm going to look at it and go, alcohol. That looks like a needle at 1600. I'm already going to guess that this is a C double bond C and this is an OH alcohol. I'm already looking at the top one. It's prop-2-ene-1-ol. The infrared spectrum of one of these compounds is shown in figure 4. All right. It's that straightforward. I didn't even read the question. I knew that was about prop-2-ene-1-ol because that's the alcohol peak there with its broad shape, and that is a needle at 1600. State the bond that you use to identify the compound and give its wave number. Right, so you could use either of these to identify the compound. Prop-2-ene-1-ol, bond used to identify compound. You could talk about this one. The bond used to identify